All right, so thank you, Sylvia, for the generous introduction. Also, I would like to thank Frank and Frederic for the invitation to be here today. It's a real pleasure to be among this crowd because you are experts in what I'm going to talk about, and I'd be happy to get any form of feedback on what I'm going to present. So what I will present today is something which I have started doing my PhD 20 years ago. And when I finished, I was a bit unhappy about the outcome, about some part of the outcome, and I didn't work on it for 15 years, and a bit by chance I came back to it, and I think providing a better answer. So the take-home message is that don't give up, and sometimes good solutions end up arriving, sometimes quite late. All right, so today I'm going to talk about distributions, okay, and I'm going to look at various ways of measuring distance between distributions. And so this is, as clearly you know in this audience, this is a common task in many areas of data science and machine learning in particular. And let me just give a few, like model fitting. So you want to minimize the distance or divergence between your data and your model. You may want to test independence of homogeneity, and this is naturally cast with distance between probability measures. You may also, in certain contexts, quantify the loss of information, particularly if you do like communication or privacy. And finally, some tasks in inference are cast as measuring independence. So what are the difficulties associated with it? The first one is that if you have like Gaussians or like binary random variables, it's quite easy and everything is easily computable. But as soon as you go beyond and you work with vector spaces in high dimensions, then you need to take care of non-linear dependencies, and this is quite difficult. Second difficulty is that you need to estimate those quantities, okay, typically from data. And the last part, which I think is a key aspect of this talk, is that in some setups, you want them to have some meaning. Okay? If the distance is 1, what does it mean? Okay? And this is what I'm going to talk about today. So this is clearly not a new problem in mathematics or engineering. So I've divided the world in 3 parts. Okay? So I'm sorry if your favorite way of measuring distance is not among those 3 parts, and but at least you can divide them. Okay, I divided them into 3 parts. The first one, the first way is using like information theory with the classical quantity, the Kullback-Leibler divergence, and this has extensions to various F divergences, of course. And this is just a formula for discrete random variables, where P of X is a probability mass function. So this is all very nice. This has very nice properties in terms of invariance by reparametrization. This has also strong physical interpretation in terms of physics, also in terms of communications. And this has very importantly with probabilistic inference, and I come back to that later in the talk. But it's hard to estimate beyond small discrete random variables or Gaussians. There is another way of measuring distance. So here in my talk, distance will be taken in quotes. Okay, it's a measure of dissimilarity. So, you can use optimal transport, and this was not invented by Perret and Couturier, but there's a very nice book about it. So if you want to learn about the topic, really read that book. And here there's also a somewhat physical interpretation, where it's a cost of measure the cost of transporting some mass. Okay, so I'm not going to talk about it today. There's a whole like books and talks about it, but it's also hard to estimate in high dimensions. And also, to me, the physical interpretation is a bit you have a figure, but an optimal transport distance of 1. What does it mean for your problem? Is a bit unclear. So what I'm going to do today is to look at all the techniques which are trying to measure distances between distributions through moments. So what is a moment? So I'm going to look at generalized moments, where I have a map, a phi, from my input space, whereby data is living, to some Hilbert space. So you can think of RD if you prefer. And typically you put like phi of x, in one dimension is x, x squared, x cubed, and so on. It can be anything. And once I have a probability distribution on my input space, I compute the so-called mean element, which is just the expectation under P of phi of x. Right? So what is known about that way of measuring distances is that if you take the moments large enough, so if you take all monomials, then this is characterizing the distribution. Okay? And once you have this mean element, which may live in an infinite dimensional space, then you can typically measure the distance between those mean elements. And since I have assumed some Euclidean or Hilbertian structure, I just take the norm associated with my space. Okay? And it's often called the maximal mean discrepancy in machine learning. Okay? But this has also different names. So the nice aspect is that it's easy to estimate. Okay? And you can even, in context where phi is high dimensional, you don't need to map the data explicitly. You can use the kernel trick, which I will come back to later, to estimate this in like a polynomial time in n being the number of samples. It's easy to estimate. There is no curse of dimensionality in terms of the sample size. It goes down. This goes down to the once you estimate the true one with a rate of 1 over root n being the number of observations. And this is all nice. This has many applications. There's a very nice paper by Muande and colleague, and this is used like in many areas in machine learning. But to me, what's missing here is a link with information theory. Okay, so what does it mean to have this equal to 1 is totally unclear, and the goal of the talk is to try to take those techniques based on moments to a framework where this starts to have a meaning. So the key, not novelty, but the key point about what I'm going to present is simply not to measure the mean element, the expectation of phi of x, but the covariance associated with this same feature. Okay, so the non-centered covariance. I'm not going to remove the mean. I'm just going to consider the expectation of phi times phi star. So here I'm going to use complex numbers. So star is a conjugate transpose. So if phi is a vector of size d, this is a d by d matrix. Okay, and if you are in infinite dimension, this is just an operator, but this is not going to make a difference. So by construction, phi times phi star is a symmetric, self-adjoint. It's also positive semi-definite. And then I'm going not to use a mean element, mu p, but this sigma p. And the core of the talk will be to use notions of divergences which are well known, the so-called von der Meijn entropy, trace of sigma log of sigma, or as the associated relative entropy. Okay, the main core of the talk is take this, apply that, and see what you get. Okay, and so the main properties I'm going to consider, and so it's not a new idea to take like covariance operators and apply various divergences to it. There is nice work by Girardeau and colleague and Min. But here what I'm proposing is an explicit relationship with information theory, and then various properties which are interesting if you want to apply them in practice. You can estimate them in 1 over root n. You can use them in multivariate modeling, and there is a nice connection with variational inference in probabilistic models. Okay, so this is the main goal of the talk. Let's get to it. Okay, so I'm going to assume that I have some phi, some feature vector, and when you look at kernel methods, you always have two ways of seeing the feature vector. Either explicitly, okay, phi of x is x, x squared, x cubed, and so on, or only implicitly through the dot product of phi of x times some phi of y. Okay, so there are always two competing views, and in this talk, I will use the two views. Either, so I'm going to use, for example, like complex exponential. Phi of x will be all the complex exponential of the Fourier components of x, or the dot products. So when you have the dot product, then if you take k of x, y being phi of x times phi of y, it is a so-called like positive definite function where all the matrices of pairwise evaluations are positive semi-definite. So I'm going to assume that this is the case, that the underlying space is compact, and I have normalized features. Okay, either K of xs is less than 1 or equal to 1. Maybe easier if it is equal to 1. So as I've mentioned, as soon as you have such a kernel, you know that there exists such a feature map phi. It may be hard to construct, but there exists such a phi such that K of xy is phi of x times phi of y. Okay? And often, once you have that K of xy, you consider all the functions which are linear in phi, okay, of the form f times phi of x. And this is a space which typically has nice properties. So if you take space of square integrable functions, the sublet space of functions which like square integrable derivatives, this is such a space. And so many spaces with like nice regularities can be cast in this form. And the key aspect here is that because of this like so-called kernel trick, you can look at those functions, which is a complex object, as simply like linear regression. Okay, I have some phi of x, which is explicit or implicit, and I just have f times phi of x. So I do as if I was doing linear regression. So the key here is that depending on the kernel, you can the space of functions which you can define can be small or large. Okay, so if phi of x is just x, for example, you just have linear functions. If phi of x has x and the x times x, you get quadratic functions. And the key here is that since you want to characterize distributions through moments, you want phi of x to be quite large, have many moments or many functions. And what I'm going to assume is some form of universality, is that phi of x is infinite dimensional and has a lot of components. And technically, this means that this space of function is dense in the set of continuous functions. So classical example, okay, that people use a lot is the so-called Gaussian kernel, where you have K of xy just the exponential of minus the square distance plus some width over there. And here, what you can show is that the space of functions which you obtain by doing f times phi of x, well, phi of x here is very hard to write down, but you know it exists, are just very smooth functions. So this is the first view where the kernel is there and phi of x is implicit. But if you prefer, and I'm going to do that for the rest of the talk, I'm going to use concrete example, the torus 0,1 to the d, with a kernel which is translation invariant, which depends only on the difference between x minus y. And q here will be a one periodic function with positive Fourier series, q hat. And you can then define explicitly what phi of x is. Phi of x is, as I've mentioned earlier, you take all the frequencies on the grid. Okay, you can just take the grid because I've assumed like one periodicity. You take the corresponding complex exponential, okay, and then you add some normalizing factor, and this is your phi of x. So it's an infinite dimensional vector indexed by omega in Zen d. So now you can check, first you can check that you can compute phi of x times phi of y. Okay, this is simply by taking the sum over omega, which you can compute if you want. But now you can look at what it means to have some covariance operator here. So if I take sigma p defined like this, and I write phi of x using my complex exponentials, sigma p is the element omega prime of sigma p, is simply the exponential, it just depends on the characteristic function of p. Why? Because you have the expectation of this times this for omega prime transpose, and you get back the characteristic function. So in a sense, for that particular example, you can think of the covariance operator as being just putting the characteristic function in a matrix. Okay, and here in the Toeplitz matrix, because you index all the elements, you take a value of the characteristic function only with omega times omega prime. So if you add anything to omega and the same thing to omega prime, it doesn't move, and you end up with a Toeplitz operator. Okay, so this is really a specific way of representing the characteristic function if you wish. Example that we're going to use, you can take q hat being the exponential like that, okay, and you have the exponential decay. You can check or look at the paper that for that q hat, you can compute K of xy explicitly, like this. Of course, and this is one key aspect of kernel methods, you can choose whatever x you like. Okay, so often when you teach or give talks, you take X, which is simple, like the torus, the interval, or RD. You can also take finite sets. Okay, in the context, finite set, if you use a one-hot encoding, where if you have D values for your finite set, and you map X to the canonical basis, it's a one-hot encoding, then you can check that sigma p here will simply be a diagonal with a probability mass function in its diagonal. Okay, and finally you can use other types of sets. Okay, if you prefer. But I will mention this later. For most, this was fashionable like 20 years ago when I did my PhD. Give me a set, distributions, images, graphs, whatever. You can define kernels which are adapted to that set. Okay, so this is a way to extend information theory to beyond classical sets like these ones. All right, so let's look at some properties of these covariance operators. Okay, so first property, sigma p is positive semi-definite. It's almost by design because phi times phi star is positive semi-definite, so I take expectations, so it's also PSD. The trace is less than 1 because the trace is simply the integral of the norm of phi of x squared. And I have assumed like normalized features. So as an operator with finite trace, it has a sequence of eigenvalues set into 0. And because if you assume like density, like universal kernels, the map from P to sigma P is injective. Okay, very much like the map from P to the mean element was injective. It's simply the same thing. So in fact here it is just the mean element where phi is replaced by phi times phi star. But now I can use the particular structure and consider specific divergences. And I'm going to consider the one based by the von Neumann entropy. So what is it? So if you give me a matrix A, like symmetric or Hamiltonian matrix A or operator A, then it has a set of eigenvalues, lambda A. And if I sum lambda log of lambda over those eigenvalues, then I get, by definition, the trace of A log A. And this is known to be a convex function, used a lot in quantum mechanics. Since you have a convex function, you can define the Bregmann divergence associated with that convex function. So you simply like, whenever you have a convex function psi, you define psi of A minus psi of B minus this term, which is just the difference between the function and the tangent at B. It's always non-negative. It's always convex in A. Okay, and this is used a lot in many areas of optimization and data science. And this is what I'm going to call the Kublak-Leibler divergence, or von Neumann divergence, if you prefer. So what are the properties of that object? Okay, some of them are simple and easy to prove. Like the one I've mentioned is it's non-negative, like all Bregmann divergences, equal to 0 if only A equal to B, because function psi here is strictly convex. This is quite reasonable and simple enough. But a key property is that it is jointly convex in A and B. Convexity in A is obvious because it's simply like a trace of L of G plus some linear term. But the convexity in B as well is totally non-obvious. And in fact, there are multiple proofs which originate all from quantum information theory. And this is really important property I'm going to use like in the next slide. And this has many applications. Okay, first, if totally unrelated to my talk, but I think I should mention it, all the nice matrix concentration inequalities by Trop and colleagues are all based on the joint convexity of the von Neumann entropy. So this is really a nice property. It's also used a lot in optimization. All right, so why is it nice for us? Because since I have a jointly convex function, I can use Jensen's inequality. And I'm going to use it in 2 slides, I think, in fact. 3 slides, maybe. All right, so what am I defining? I'm simply defining, okay, I have those covariance operators of matrices sigma p, sigma q for my distributions p and q. I have my von Neumann relative entropy. So I define simply the kernel relative entropy as being this von Neumann entropy applied to those covariance matrices. Okay, so it's a really direct definition. So a few properties. So this is finite under general conditions. So if P and Q are not to mean, this is finite. It's always non-negative by construction because it's a Bregmann divergence like this. you get equality if only if sigma p is equal to sigma q, but because I have assumed that the map from p to sigma p to be injective, it's only if p is equal to q. And it's also jointly convex in p and q. Okay, so we start to preserve some nice properties of the classical Shannon relative entropy. Okay, those two are shared by the Shannon relative entropy. You can extend this to the non-relative entropy to define a notion of entropy, but as is common, if you have like continuous spaces, it's a bit of a pain to normalize. So I'm going to not mention it today. You can look at the paper if you prefer. So maybe a spoiler for the rest of the talk. Okay, so I'm going to preserve some properties of the Shannon relative entropy, but not all of them. The reason why is if I preserve too many of them, I have to be the Shannon entropy because of nice axiomatic definitions of the entropy. Okay, I'm going to miss one, okay, and for the experts, I'm going to miss like conditioning. Okay, entropy is well adapted to do conditioning. I'm going to miss this a bit, and I'll mention it briefly later in the talk. All right, so let's look at the relationship with entropy. Okay, this is what the goal of the talk is, to see if that quantity here can be related to the true entropy between P and Q. So let's look at the simple case first. Okay, I've mentioned the finite set with the orthonormal embeddings. So I map X to phi of X, and if I take the element of the canonical basis, okay, then the orthonormal embedding. In that case, like you can, all covariance operators are diagonal or they are jointly diagonalizable. So essentially, they are characterized by the diagonal or by the eigenvalues. They have the same eigenvectors. And then my notion of kernel entropy is really the classical relative entropy. Okay, so this is very well known. But the question is, does it extend to finite sets? Okay. So this is what I'm going to show now, is that it's not going to extend exactly to finite sets, but I'm going to have a lower bound. Okay, so this is maybe there will be two technical slides in the talk. This is one of them. All right, so let me look at the definition. So this is the definition of my kernel relative entropy. Okay, so this is sigma p over there. This is sigma q over there, written with the density of q with respect to p. Okay, and now what I have here, I have the convex function d taken at the expectation of phi star over dp and this over dp. So I can apply Jensen's inequality because d is jointly convex. This is where the joint convexity is really important. And then I can take the dpx outside. This is Jensen. Okay, so this is just applying Jensen. Now I can start to reorder things. And first, I notice that now my two operators here are both rank 1. Phi times phi star is a rank 1 operator with many zero eigenvalues and one non-zero eigenvalue, which is like the square norm of phi of x. Same thing here. This is a rank 1 operator with the same eigenvectors, but a slightly different eigenvalue. So now I can look at so those two are commuting, so I can simply sum over the eigenvalues. The ones which are 0 don't contribute to the sum because 0 log of 0 is 0. And I just have to keep the eigenvalue, which is non-zero, which is this one for the blue one. And this is a p log p over q. Okay, so I get this eigenvalue goes to there. Now this will cancel, okay, and I use that phi of x is normalized. And I exactly get the von Neumann relative entropy. Okay, so here, this shows that this quantity that you can define regardless of any link with information theory happens to be a lower bound on entropy. It is equal when I have orthonormal embedding, but otherwise it's just an inequality. The question is, how tight is it? Okay, and let me provide another inequality in the other direction, but now I'm going to need to make some assumptions, okay? And in particular, since I know I have equality between this and that for orthonormal embedding, there has to be a notion of how close to orthonormal my embedding is. So there has to be some form of that. And this is like, let's give me the approximation bounds, so not with all details, but you can have the details in the paper. So what you can show that if you put some basic assumptions on the densities, then you can bound the difference between the true Shannon entropy and the one I'm defining is positive because you have a lower bound. And then you can show that you get some product of two terms, one which is depending on P and Q, and one which is characterizing the lack of orthogonality of the embedding. So for that type of result, I had two proofs. I first made a proof of 10 pages, which was like very complex, very long, and I was proud of it, but it was very long. And then by reading books in quantum information theory, I get a two-line proof, which I'm going to present. And I was both disappointed and happy, you can imagine. And so the idea is to use like quantum measurements, okay? So I'm going to take tau being like a uniform distribution, okay? It can be uniform of my compact, okay? It has to be fixed, it can be anything. And I'm going to define for all elements y in my input space a measurement operator. And for those of you who are familiar with quantum mechanics, what is a measurement in quantum mechanics? It has to be a PSD unit trace operator. Okay, so let me define this PSD unit trace operator d of y. Okay, then no unit trace. It has to be PSD, and the integral has to be equal to identity. Excuse me. All right, so this is the operator. I take my feature map, I normalize by my covariance operator associated with tau. You can check that if you take the integral of that over d tau, this will lead to sigma, and the two will cancel to get identity. So it's a quantum measurement. So the measurement is applied by taking my covariance operator sigma p, trace with my d of y, and this is my measurement, okay, which I call p tilde of y, depend on y. And the key here is that if you look at the formulas for this d of y, and this is just p of y, just the trace of dy, this is dy, this is just p of x, okay, and then you can move the traces around, okay, and check that p of y, p tilde of y is the integral of some smoothing kernel h over p of x, where that smoothing kernel is defined over there. It's just like moving the traces around. So it's a square, so it's non-negative, and it sums to 1. Okay, so it's a bona fide smoothing kernel. So essentially, p tilde of y is just a smooth version of p of x. Okay? But now, because I have a quantum measurement, I can use the data processing inequality, that the divergence between p tilde and q tilde, okay, which happens to be exactly the classical Shannon entropy between p tilde and q tilde, is less than my relative entropy. And now I have a sandwich between the entropy between p and q and the entropy between p tilde and q tilde, and p tilde and q tilde are simply smooth version of p and q. Okay, so this is like a one-line proof, just define the proper operator, and then once you have that, you can derive the result which is over there. Okay, so I think this is I think it's a nice application of quantum information theory. What are the consequences? Okay, if I take my torus, which I've used, which I will use later also in the talk, then if I take this like type of Q hat, which corresponds to a kernel which has a decay which depends on the x minus y over some sigma. So if sigma is 0, I'm taking only x close to y as being significant, and otherwise when x minus y is much bigger than sigma, then this is 0. The kernel is 0. Then I have that the difference between my notion and the classical notion goes down to 0 as O of sigma squared. Okay, so if I get smaller and smaller bandwidth, then I get closer and closer. And of course, the big O has many quantities which may be exponential in D, but the dependence in sigma is in sigma squared. All right, so this is just showing that this notion is not too far from the classical entropy. Another problem, in a sense, is that that notion, let me write it down here, is, where is it written? Yeah, so it's a spectral function, okay, of an infinite dimensional operator. Okay, so this may be hard to compute. Okay, and this is where kernels come to the rescue. Okay, and so I'm going to what was written there. I'm going to assume I have n ID samples of P, and I want to compute an estimation of that quantity. I'm going to focus only on the complex part, sigma p log of sigma p, and I look at the paper for the other aspects. The question is, how can you estimate trace of sigma p log of sigma p? So there is a natural estimator, okay? Replace sigma p by the empirical covariance matrix, which I will call sigma p hat, and just replace this by that, and then it's a natural estimator, okay? So there are two good things. First, it can be computed easily, and this is a very classical trick in kernel methods, which had been applied to kernel PCA and to other divergences by other people before, where you can show that the eigenvalues of sigma p hat are the same as the ones of the kernel matrix K divided by n. Okay, so K is a matrix of pairwise evaluations, and they have the same eigenvalues, so that trace is equal to that trace. And the benefit here is that K is n by n, so you can compute eigenvalues. This is still costly because it's cubic in n to compute the spectral function, but there are many ways of, you have 20 years of research in kernel methods to make it faster if you want to lower the cost, okay? So you can compute it, nice, but does it do what you want? In particular, since K will have a decaying spectrum, what happens around 0 could be a problem, okay? Because you get like 0 log of 0, you may have some instability around that. And the answer, in fact, it is not, so don't look at that. What you can show is that the difference between the estimate and the true value in some like in expected deviation goes down to 0 as you get more and more observations n. And it is controlled by this dominant term here, which is the larger term in practice, which is of the form square root of C over n, and C as an explicit control. And for the experts in kernel method, this is a so-called, it's often called the maximal leverage score, okay, in the kernel methods. And it happens that if you can control the integral of the leverage score with respect to the regularization parameter, then you get a control. And the key here, there is no need to regularize, just a classical estimator that the simplest you can think of as the good properties. So let's try to see what it means on my torus example. And for that torus example, you can compute that quantity, okay? And it turns out that it's of the form sigma to the minus d. We can compute it, so it explodes in dimension, and this had to happen, okay? I would not have been able to get rid of the curse of dimensionality. Why? Because it's known that to estimate the true entropy, you need to have the curse of dimensionality, so I can't avoid it. And this is where I recover it. So now this means that if you take that estimate into this, that you can estimate up to that term, okay? And I've shown earlier on that that element is essentially O of sigma square close the true entropy. So now I have sigma square on one side, I have that term on the other side, and I can adapt sigma, okay, as a function of n to make it like as small as possible. And if you do that, you get to a rate for entropy estimation and for the true entropy, the Shannon entropy estimation of that term, okay? N goes down to 0 as n. Oh, this is normal, the least you can expect. It's quite slow, because 1 over d type of behavior. It's not optimal, because the optimal one is of that term, of that form, but it's reasonably close. I was quite happy that it was not too far away. Right, so you can estimate for finite sample. So just basic simulation, just to highlight the fact that you can run things on a computer. Okay? It's not simply like math without any possibility of application. This is just like a very simple example in 1D. Okay, just to remember the result. I have some entropy estimates, okay, which are all higher because entropy is minus the relative entropy. So the true one is the black one, okay, and I'm looking at various kernels with different bandwidths, sigma, and I add more and more samples and I estimate. And there are a few things to look at. So as I get more and more samples, when n is increasing, I get closer and closer to the limit when n goes to infinity. It's just the statistical effect. The more the data, the better, the closer I get to my limit. But the limit is always below. Why? Because I have this lower bound effect. And as I get smaller and smaller bandwidths, okay, when sigma is 1/4, I get closer to the true one. Okay, so this is just highlighting the fact that when sigma gets smaller and smaller, you get closer and closer. Okay, just so this is 1D, but you can do simulations in any dimensions, and people have done this. Since then. All right. So in the let me now present what you can do with it. Okay. So in fact, the motivation for my PhD was to measure independence. Okay, it was the glorious year of independent component analysis, and people were measuring independence. And what I was doing then, which was wrong, okay, don't tell my advisor, but this was wrong, is that what many people would do will take, I have two spaces x1, x2, I have two feature maps phi1, phi2, and the simple idea was to concatenate them. I take phi1 and phi2, okay? I do concatenation and doing like operator on that concatenated object. It turns out that if you really want to measure independence or to get the full dependence, it's better to take all the tensor product, okay, of those two spaces. So all the product between phi1 and phi2. This is much richer, and this allows to get a stronger behavior. And this is what's done in quantum mechanics. Okay, so I don't know much about quantum mechanics, but if you have two states, then if you observe two states, this is what you need to do. So you have this tensor product. So you get a covariance operator for the tensor product, P of x1, x2. You get 1 for x1, 1 for x2. Okay, so if you want to measure independence, then typically, if you use the material information, you take the Kernel divergence between the joint and the product of marginals, and this can be mimicked for my case as well. This is a joint covariance operator, the product of marginals, and it turns out that it shares many of the properties of the classical mutual information. It's non-negative, okay, equal to 0 if only if x1 and x2 are independent. Okay. So it's not a lower bound on the true one. I forgot. I don't think so. So now, if you measure independence, okay, you may want to check if it measures conditional independence. And this is where things fall apart. Okay, so it's known that if you have a data processing inequality for the Shannon entropy, that the entropy between the joint is bigger than the entropy between the marginals, with equality if only if the conditionals are equal. Okay, this is like the last property that you need to be the Shannon entropy. And this one I don't have. Okay, I don't have the NAS conditioning, so you can discuss it later if you want. But this is the moment where I cannot be the entropy, the true entropy. Other application is to do inference. Okay, so there is a very nice like Donskoy-Varadhan inequality, which states that the log partition function. So if you give me a function f, and distribution Q is just a log partition function. The integral of e to the f to the log is the Fenchel conjugate of the relative entropy with respect to the first argument. Okay, so this is a classical inequality, well, classical equality in information theory, and this is a core of many developments in inference. Okay, if I give you a density f, okay, and you want to compute various moments of the Gibbs distribution associated with f, okay, a key task is to compute this log partition function and its derivatives. And since it has some variational formulation, if you approximate this problem, you get an approximation of that, and the minimizer or the maximizers here will be also approximate. Okay, this is a core of variational inference, and there's a nice review paper by Wainwright and Jordan. So now, since I have some lower bound on that, I can simply replace this by its lower bound. Then I obtain an upper bound on the log partition function, and this is essentially what can be done. Okay, so you just define the exact same problem, but replacing this by its lower bound, you get some upper bound. And if f is a quadratic form in phi of x, then this quantity depends only on sigma p of that form, and then you can compute this quantity with a semi-definite program. So this can be done in polynomial time. I won't give you details, but this is one way to do variational inference here. So simple example, okay, just to highlight the fact that this can be computed, okay, and now we have simulations in higher dimensions. If you take like something f of a similar size, very simple like potential, this is the value here. You can take some feature space based on the finite number of exponentials, and as you increase the number of frequencies, then the approximation gets tighter and tighter. Okay, it's just to highlight the fact that we don't never get exact, but you get closer and closer approximation. All right, so maybe a few last points before concluding. So what about the relationship with optimization? Okay, in fact, this was the motivation behind the work. Is in many instances, when you do like physics or statistical estimation, you add a temperature, okay, epsilon. Okay, so you look at the Gauss distribution where epsilon, you add the temperature epsilon may go to 0. Okay, so what you can show is that if you add epsilon and put the epsilon back in here, then you get the exact same variational formulation with an epsilon over there. Okay, and the key is when epsilon goes to 0, but the temperature goes to 0, it is known that the Gauss distribution gets concentrated at the minimizers of f. And this can be seen by simply like getting rid of that term, and you see that this has to tend to the supremum over all probability measures of the integral of f over that probability measure. And this is maximized when the measure is concentrated at the maximizers of f. So at the end, this will tend to the supremum of f. Okay, it's a very classical property. If I take a log sum exp with a temperature, then it goes to the maximal value. So this is well known in the general case. Is there a meaning in the context of my kernel entropy? And it does. Okay, so I'm going to summarize like a lot in a few lines. But what you can show is that essentially by replacing this by my kernel relative entropy, you end up with a formulation which is very similar to this one, but you instead like maximize that object, which is simply the integral of f dp if f is a quadratic form. But now you don't maximize it over all probability measures. That will be for p sums to 1, I keep it, and p is non-negative, but you only assume that the covariance is positive semi-definite. So if p is a positive measure, this is a positive operator, but not vice versa. Okay, and it turns out that relaxation, replacing p non-negative by p having a non-negative covariance matrix, is at the heart of what is called sum of squares optimization, which was launched by Jean-Bernard Lassalle and Pablo Parillo like 20 years ago. And if you want to know more, we have a paper with colleagues on that. And in fact, I started to work on this as a way to get algorithms for that. Okay, it's a bit backwards, but this is how we ended up doing it. Right, so in a sense, if what I'm proposing here is like doing sum of squares, but with a probabilistic flavor. Last point, I have 3 last slides now. So now I have a lower bound. Okay, so I've been told by my advisor, okay, it comes back again, that if I have a lower bound, if I maximize it, I'm better and better. Okay, and for this, it's better if you have some nice properties about concavity or convexity. Okay, so if you want to optimize the kernel, it's easier if you are concave in the kernel because you maximize the concave function and things are easy. And it turns out that it is concave in the kernel. Okay, so the funny story that I thought it was convex in the kernel, and I managed to prove convexity, and the proof was based on 2 mistakes. I had a MATLAB proof or a Python proof, which I had inverted, and I had applied Jensen's inequality in the incorrect direction. Okay, this happens to the best of us. Okay, and when I wrote down the proof carefully, I realized that it was in fact the other direction, and it became concave, which I wanted. But so be careful with Jensen; it's often the incorrect direction. So because it is concave, you can start to maximize over the kernel. Okay, you can make the bound tighter and tighter. Okay, if you wish, and I won't give detail, but this is like a nice property. Okay. Nice property like that. So a few extensions, okay? So as soon as you get think about the Kernel divergence, the F divergences are not so far away, okay? Those are the divergences of the form integral of F dp over dq times dq, okay? So in my case, F was t log t minus t plus 1 for the Kernel divergence, but you get any function for which F is operator convex, so this is like a bit more than convex, and then everything I've described so far is still is preserved. Then you can have other and better notions of quantum divergences, and in fact this is a nice suggestion by Omar Fauzi from ENS Lyon. So I cited the paper and he said, but you have lower bounds, but it's known that there are like better quantities in quantum, the quantum world, which is that quantity, okay, which is the same as this one if A and B are commutative, but which is different. Directly convex, not obvious, and always better. So essentially, if you take what you had before and replace this by that, you can only do better, okay, which is true. And this is what I've done later. Then no, let me forget about that. So a few discussion points, because you probably wonder, maybe some of you have some questions about that. Aren't you just doing Gaussian in feature space? Okay, so this was something which was fashionable 20 years ago. You take a problem, okay, map it to a high-dimensional space, okay, through phi of x, and do some classical things in the feature space. And classical things are linear methods or Gaussian assumptions. It is not true, because if I were doing this, I would get the classical like Stein divergence between like covariances, which is not what I'm using. Then you may wonder, are there any links with quantum mechanics or quantum inversion theory? And there is, in fact, there is one, because I took a class by Roger Ballion like 30 years ago, and I looked at the polycopier, at the class notes, and there was everything that I needed to know about like von Neumann entropy, but I had never realized it. But beyond that, like class 20 years ago, I have zero knowledge whatsoever of quantum mechanics, and I don't exactly know if there is a formal link with some physical system. One thing which is like very specific to my problem is that my sigma p here, okay, there are trace class operator, because the trace is equal to 1 if you have normalized features. There are PSD, but they have to be of that form. Okay. So for example, if phi is my set of complex exponentials in 1D, it has to be a Toeplitz operator. So it's an operator, often called a density operator in quantum mechanics, but with very specific properties. It has to be in the span of phi times phi star. And this creates a lot of differences. But if you have any idea on how to make a closer link, I'd be happy to. And also, I've been told that there may be some link with quantum computing, but I have no clue of how. So if you have any ideas, I'd be happy to discuss. All right, so let me conclude. So the goal of my talk was to present a very simple measure of distance between distributions, whose idea is quite simple. You just take covariance matrices and apply the von Neumann relative entropy. But the key novel aspect is that it has a direct relationship with Shannon entropy, just by using Jensen's inequality. And this can be applied to various things. So I'm coming from machine learning. Inference is one key application. But probably in this room, you have many other ideas, and I'd be happy to discuss. So in terms of extensions, I have worked on doing larger scale experiments. Clearly, so it's not ready for conquering the world immediately. Okay, this still has to be like pushed back in terms of numerics, and this is what I'm actively doing. What I would like to highlight is the fact that I focus on my talk on simple sets X, but you can define kernels on anything. Okay, graph, images, distributions, sets. This is you have whole books written about it, and so this means that you can use tools from information theory on those ones. And there's already some nice application to measuring like loss of information in differential privacy. A few references, and on this I will thank you for your attention.
Thank you for this very interesting talk. Are there questions?
I will go.
Thank you. You showed you explained the distance between two distributions. Mm-hmm. What happens when you replace the distribution by the empirical distribution?
So this is what I did here essentially. So if you do that, so for that term things go well, okay, because it's you get this spectral thing. For the joint term, it's a bit of a pain because the two distributions, if they are discrete, will be singular to each other. Okay, and then you have to do a bit of regularization. Okay, so if you know sigma q, so if q is known, it's like if you know it's uniform, and it's easy because you know the moments. But if both p and q are empirical, you have to do an extra thing to make it work.
Sylvain, I have a question.
Sorry.
So what happens if the example are more difficult, image, movies?
Oh, so you can, okay, so what remains, you always get an upper bound, a lower bound of the true value. Is it meaningful? I don't know, okay? So this is to be looked. I know that there is one researcher in Princeton who has been looking at that, at the measure between images, but I don't know exactly what you would get. But yeah. So with a lower bound of entropy, you want to make it as tight as possible, but beyond that, it's unclear.
So when I look at your function phi at the very beginning, from a set to a Hilbert space, yeah? This reminds unitary representation of a group. So really, for in case of images or other, can you use this type of instrument to put some invariance in your method?
Indeed. So in fact, for the entropy case, having some symmetries and group invariances helps a lot because now you know that the eigenvectors are compatible with the symmetry and so on. But that's a good suggestion. I've not explored precisely how you would incorporate all invariances, but it's clearly something of strong interest. So if you have some invariance in the input space, how does it transfer to sigma? I think this is like, I don't know how exactly, but good suggestion. Yeah.
I have a question on a remark. If you come back to your slide on with temperature,
yeah.
Yes, this one. So in physics, especially Roger Balian, he don't like this one. So if Q is a uniform law, so you could it will play the role of entropy. Yeah. So you have here it will be the free energy. So energy minus the temperature by the entropy. But in fact, the good potential is not this one. Is the Massieu potential. So François Massieu was from Cordemine. And if you divide by temperature, so here you will have the inverse of temperature by the energy minus the entropy. And this is a Legendre transform with two parameters: the inverse of temperature, which is the Planck temperature, and the energy. And so the remark of Balian is if you use the free energy, you lost the Legendre transform. And what is important? And the good parametrization is the inverse of temperature, the Planck temperature. And the story is very funny because it was a reviewer, it was Bertrand who has reviewed the paper of Massieu. And Massieu has parameterized by the inverse of temperature. And Bertrand say, no, I would like to parameterize by temperature, and we have to wait Planck to understand that the good parametrization is the inverse of temperature. So I invite you, Roger Balian has made a paper on the website of Académie des Sciences
I'll ask him,
on the Massieu potential, and you have an archive in École des Mines on Massieu.
Okay, I'll look.
Now my question is that in information geometry, so I know that you know also the book of Rajendra Bhatia. So on the cone of symmetric definite positive matrices, we have another metric also for these matrices, which is a link to the to the trace, the sum of the square log of the extended eigenvalue between the two matrices. Is there some links between this distance and?
I have no clue. I think this is. Haven't you used this once?
Yes.
Okay. I'm surprised because the two. No. Probably you can extend this to that class of matrices. The key question is, does it have a meaning for P and Q? Because you can always take any measure of dependence between two PSD matrices, but because mine are specific, they are covariance matrices, it has to have a meaning for P and Q directly. Probably it has, but is this meaning a classical meaning or a new meaning? That's a different story. But I'll have a look. Yeah, thanks. Yeah, that's good.
Maybe we have time. Yes.
Hi, thank you. I have just a short question regarding the adding of temperature.
Yeah.
Do you think it is possible to introduce considerations like that by introducing some deformation on the level of quantum C-star algebras? So you introduce some dual number on that level abstractly, and this will take the role of the temperature because it really looks. So you want a small epsilon there, and that's how the infinitesimal stuff working in the.
I would be very happy that going from zero to operator is like adding some noise in a quantum world, but I have no clue if this has any meaning. Okay, but if you have any idea in mind, please come to me after the talk because I'm totally non-knowledgeable in quantum mechanics, apart from having one class long ago.
Thank you.
I have a last historical remarks. The story of the characteristic function. The characteristic function in statistics has been introduced in the lecture at Sorbonne University by Henri Poincaré. And why he has introduced that is because the previous lecture was on thermodynamic, and he has read the paper of Massieu. And Massieu has introduced what we call the Massieu potential, but also the notion of, we say, characteristic function of Massieu. And so it's because Henri Poincaré has read the paper of Massieu on characteristic function in thermodynamics that he has introduced this notion in statistics. So it's so the notion of characteristic function comes from Massieu in thermodynamics.
Very good, thank you.
Is there a last question? Well, I think we can thank the speaker again.